Yeah, as the title says, everything you always wanted to know about ontologies, but were afraid to ask. This is, let's say, abbreviated or very much abbreviated version of a talk that usually lasts 90 minutes and has especially been adapted, of course, at least a little bit to material sciences. So I often give this talk also for people from the humanities, then with examples from the humanities and so on. And as we have seen already in the poll, one of the main reasons for people being here is getting to know a bit more about ontologies and getting a bit better familiar with it and see where are the limits and stuff like that. We will briefly talk about that, but of course we can't do it exhaustively in only 20 minutes. However, I try to give you a quick intro and overview of what ontologies are all about. So the ontology experts among you, lean back, relax, and just listen and see what you already know. However, okay, let's start. And some of you already might have seen one of my talks, and usually I start with a slide like that and ask, okay, what do you see here? Of course, it's a number. So we are dealing with data, so let's assume it's some kind of data. What could it be? 14. Since I only see my screen and don't see the chat, sorry, I can't see whether you have already interesting suggestions for that. But it could be anything, you know, it could be a number, it could be some measurement. But if it's a measurement, then of course the question is, yeah, where's the unit? So if we have a unit, then things become a little bit clearer. So it's 14 meters, can be anything, can be a length, of course, could be, I don't know, circumference or whatever. So if you see this one, then yeah, looks like a length. What is 14 meters long? And you have heard about it, let's say last week. Yeah. Long story short, this is the diameter of this G-2 storage ring magnet at Fermilab, and probably many of you heard in the last week that there was this great G-2 experiment that at least now gives hope that there is physics beyond the standard model available. So there seem to be, since their measurements in the experiment deviated from the prediction in a significant way, so that there is room for more particles somewhere and also room beyond the standard model of physics. And therefore, this is a number which is related, of course, to a rather important, let's say, scientific event. However, this is only the diameter of that storage ring. So to describe the experiment exhaustively with data, of course, this required an immense amount of data. The example serves one purpose, simply to tell you that if you have the data alone with no description and you have no idea how this data interacts with other data, it's raw, which means it's more or less useless. So you can't do anything with it if you don't know what the data really means. So what is the data about? And how does this data that you have relate to other data? As soon as you relate it to other data, if you have relationships among the data, if you have, let's say, connected to another data and say, yeah, this is longer than that one, this is higher than that one, and so on and so on, data becomes information, which might be already useful, but not necessarily has the purpose of being useful. It becomes useful as soon as you put more semantics, this means meaning, in it. If you put meaning in the data that you say, yeah, this is a diameter, the diameter of something completely, you know, special, and you describe what it is, and you also describe why the diameter is somehow important for having a specific, let's say, a property, then this becomes knowledge, because then you are adding meaning to it. And then it's probably also to understand, you know, the data, to put it in context. And then probably, if you go even one step further, if you try to identify patterns in your knowledge, you will be able to make predictions about, you know, situations that haven't occurred so far. And this is exactly where we want to go. And there is this pyramid that Chris already showed. So we go from data via information and knowledge up to wisdom, where we want to do then in the end predictions about future behavior. However, to get there, first we have to look closer to the knowledge level, because what we want to do is we want to represent our research data we have there and connect it with semantics, so that, let's say, computer programs will be able to interpret the data in a more or less automated way, so that things like data integration become much more easier. And also then working with the data, building on top of the data, using the data to do inferences and deductions, this then will become possible. However, if you want to represent and express knowledge, the problem is people can't share knowledge if they don't speak a common language. So you need a common language to express this kind of knowledge. And to speak a common language usually means you have to use common symbols and concepts. So this usually is guided by the syntax. You have to agree about the meaning of these symbols and context. This is the semantics. Then usually you put your things in drawers, so you classify and categorize things that you have there. So you do this with the help of a taxonomy, and you try to find associations and relations between the concepts you are talking about. You can do this with a thesaurus, for example. However, this is not enough because there are rules. What kind of relations are allowed? Are there certain constraints? Which kinds of relations do make sense, which not? So these complex things usually then you can guide with the help of ontologies. And the question is, of course, but what exactly are now these kind of ontologies? Ontologies is, as you have noticed, plural. In philosophy, where the term comes from, talking about ontology means you are talking about something in singular, because ontology there is a discipline. It's a subdiscipline of metaphysics, and usually it's about a theory of being. So philosophers try to develop a theory of being, of the world like it really is, not the world like we see it with our senses. That would be epistemology. It's about how the world really is, how our mind is able to conceive the world and make, deductions and assumptions about the world. And it tries to explain the being itself by developing a system of categories in which, again, drawers, you put your things in, and also you define intrinsic relationships between these categories. So this already has started with Aristotle more than 2000 years ago, and further went on, and computer scientists adapted exactly this kind of knowledge representation because philosophers wanted to represent the entire world. Computer scientists in the early days already of artificial intelligence came about that they said, okay, if we want to do symbolic logic and want to do a symbolic representation of the world, of course, we have to look at this discipline of ontology, because people there are dealing for a long time on how to describe the world, how to represent the world, the knowledge of the world in a specific way here, so that we are able to grasp it. The only thing that, of course, was missing, philosophers do this by words. Language is, of course, ambiguous, so everybody who reads it has a specific assumption about it, putting it into context and thinking about your own experience with the world and your common sense knowledge, and you have a different interpretation of it. Of course, this doesn't suit well for a machine. What you have to do for a machine is you have to connect it with something that the machine really understands. And this is mathematical logic. So the computer scientists came up with another definition of what is an ontology, or what are ontologies, because you can have many. So there, let's say the most concise definition that you will find is by Gruber from 1993. It says an ontology is an explicit formal specification of a shared conceptualization. Meaning, conceptualization is you have an abstract model. Basically, what you do in computer science or also in mathematics, if you're dealing with ontology, you have a model that is based on a set theoretic grounding or foundations, which means you have a domain, you identify relevant concepts, and there you identify things which are classes. Classes can be instantiated, so here comes in the set theory and the set theoretic interpretation of that, and you have relations between your concepts. So this is an abstract model. It must be explicit because all of your concepts that you are referring to have to be defined. If there is something undefined, your system will not work. And it has to be formal, meaning we need a grounding in mathematical logic. So logic is the basis of these ontologies. They can be expressed in a specific symbolic language, which is usually kind of a logic. You can do this all, of course, in first-order logic. However, first-order logic is not so nicely usable if it comes to terms like complexity, computability, and stuff like that. So there are, let's say, better-suited logics, which are a bit less powerful than first-order logic. It's description logics usually. This is an entire family of logics. It's closely related to so-called modal logic. You don't have to remember that. But this is the mathematical grounding. And most importantly, if you are then defining these kind of ontologies, you need a consensus about the ontology, which means it should be clear that you are meaning the same thing by defining that kind of concept. Meaning also the purpose which you have in mind when you design the ontology, of course, you must agree upon that. If one defines an ontology, let's say for data integration, and the other one then for making predictions, this probably won't overlap and won't really fit for both purposes at the same time. Okay, so let's see how ontologies now work. Now everything becomes really explicit. Going back to our example and our 14 meters, how would we represent this with an ontology? You can do this quite easily with a graph-based model here. You say you have here your G-2 storage ring magnet, and you simply say, yeah, okay, this is a storage ring magnet, and it has a diameter. And I give here a diameter in meters. So this is only a toy example where I put the unit directly into the property, because you can also do this in a more elaborate way. I just wanted to spare you with that. We did this in the core ontology. We are using another unit concept. And there you can define that this storage ring has a diameter here of 14 meters. Of course, this property only works in meters and nothing else. And you see here also via description logic, the way how you would encode this in kind of logic below. Of course, the example can be a bit more complicated. You can say that this G2 storage ring magnet is a storage ring magnet, which is part of an experiment that is conducted at a laboratory. And if you look at the blue boxes, these are the instantiations of the classes which are given in the gray boxes. So the storage ring is located in Fermilab, which is a laboratory, and Fermilab is located in Batavia, Illinois, which is a location. And you see here a laboratory can be located in a location, as well as something else like a gallery, where an exhibit is exhibited at a gallery, is also located in a location. And you can also define that two classes don't share common or instances. You say they are disjunctive. So like, for example, we say a laboratory and a gallery, they are disjunctive, so they are not really the same. So you can deduce, for example, inconsistencies and contradictions by exactly defining these kind of differences within an ontology. And also you see here in the gray box below how this is encoded with the help of description logic. Also something you don't have to worry about. What is important, also these terms have been mentioned by Chris, we decide two sides of the story here. So most times in ontologies, you are talking about so-called terminological knowledge. This is for all people who come from databases and software engineering. Like in the database, you have a database schema. So the schema is the terminological knowledge. You define there your data schema. And if you think of databases, relational databases, there was, of course, specific semantics in it, because you could define relations and you could define tables and stuff like that. And what you could do there, you could also define keys and references between tables. And if you then go one step further to object-oriented databases, you had the nice concept of inheritance. And now you go to, let's say, knowledge bases and ontologies. And there, in addition, you have further, let's say, inferences and deduction possibilities over inheritance and stuff like that. So more than inheritance, because you saw that we can define kind of rules and constraints and all the stuff that can be fulfilled and can be checked whether they are fulfilled or not. And you can deduce thereby also new explicit knowledge out of that. The blue side here is the assertional knowledge. Chris phrased it as the data side. So you have your data there somewhere, which means these are instances of exactly these kind of classes. So the G2 storage ring magnet is of type, and it's not only a storage ring magnet, it's a superconducting storage ring magnet. And we see that this thing has a name. So the name is again G-2 storage ring magnet, and it's located in Fermilab. And if you look at the classes, so the superconducting storage ring magnet, it's a subclass of the storage ring magnet, and it's part of some kind of an experiment. The nice thing is, since you have here a subclass relation, and subclasses come from set theory, and they have already existing semantics, like, for example, transitivity rules. This means you can simply deduce by applying here logics and a reasoner that if the G-2 storage ring magnet is a superconducting storage ring magnet, it's at the same time also a storage ring magnet, since you have this subclass relationship here. And on the other hand, you can also deduce, since it's a subclass, it must also be part of an experiment, since the storage ring magnet is already part of an experiment. So this is kind of inheritance that you have here for exactly these things or these properties that a specific superclass might expose. But there is much more possible. This was only to give you a quick glance of, you have these two sides, terminological knowledge and assertional knowledge, which means you have the schema information and you have the data that is fulfilling exactly that kind or representing that kind of schema. And thereby there is implicit knowledge that can be deduced with the help of the semantics that is used to define all these things like subclass relationships and stuff like that. And by that you can draw logical inferences to make implicit knowledge explicit in the end. And to serialize the stuff and encode it and put it into machine with this is semantic web technology, which is the basis of many of these ontology things. You can encode simply these graph structures in terms of triples. So what you see here, usually you have a node and you have an arc to another node, and this can be encoded within a so-called triple. These triples are like small sentences. So you start with a subject. This is here the G2 storage ring magnet. And you say, okay, you have a property which has the name FOF name, which means this is the name of the thing. And then you come up with a string, which is the name of this thing. And you see this is easily encoded, and you can encode any kind of graph structure with the help of these kind of triples. So this is quite easy. There are different types and categories of ontologies. So doing the same thing as the philosophers, starting from the top, explaining the entire world. These are so-called top-level ontologies. They are usually rather general and rather generic, but they have the, let's say, the benefit that you really can try to put everything in there. However, they are not sufficiently detailed now to represent completely, let's say, an entire domain or subfield or subdiscipline. Like, for example, we want to represent material sciences. This would be then a domain ontology, and there we would have to encode all of the available textbook knowledge for exactly that domain. Most times we don't do that, so we want to represent a specific application, or we have a specific application in mind, which means we specialize here a specific section of the domain ontology for a specific purpose, for a specific task. Tasks can be represented with task ontologies, and then we end up in application ontologies. So this is what we usually do most times, that we focus on a specific application, and thereby we are doing application ontologies. From the level of expressivity and semantic complexity that you put into the ontology, you can start very easily with a so-called controlled vocabulary, where you don't have any kind of semantics. You only are using terms which are controlled and have a given meaning. However, the meaning is so far not necessarily defined in a formal way. And you see here there are several steps until you come in the end to first-order logics, which gives you everything from taxonomic relations, frames, value restrictions, disjunctiveness, inversiveness, and so on and so on. So you have then everything in there. These are then the so-called heavyweight ontologies. However, if you think now we know already about ontologies and we could simply start doing things, it's tricky. As you see here, it does not do to leave a live dragon out of your calculations if you live near him, as Tolkien says in The Hobbit, meaning if you have a specific application in mind and you do this not alone, if there are more people doing this, they should more or less have the same, let's say, view of the world and see that they are defining an ontology for the same purpose. Otherwise, you might end up in something like the famous ontology defined by Jorge Luis Borges as an alternative to the Linnean system of nature, so to the biology or biological taxonomy. And he said, or he claimed in a famous essay, that He found various categories of animals from a certain Chinese encyclopedia, and there the entire biology, or let's say the all animals, were categorized in the following categories you see here, ranging from those that belong to the emperor up to whatever you see there, suckling pigs, mermaids, stray dogs, etc. Those that have just broken the flower vase, or those that at a distance resemble dead flies. You can do it that way. However, the point is, the question is whether everybody then will understand you. So you have to be careful if you see ontologies as an interpretation of reality, because it's only one specific interpretation from your viewpoint. And you have to make clear that people who are using this see the world in the same way like you do, because otherwise you have, let's say, insufficient overlap and intersection there. So if you look at material scientists and what material sciences and what we do here in Material Digital, so what we did so far is we are working on a core ontology, which serves, let's say, somehow as an intermediate, or let's say something which is a bit more specific, like the MO ontology that you might already know. Rather generic and connects already to a top-level ontology, here to the basic formal ontology. Therefore, it is not as specific as, for example, we would like to have it for the purpose of, like Chris said, for example, doing or being able to do predictions, because we put many, let's say, natural science laws into the ontology if possible. However, besides the core ontology, which is on a domain ontology level, but of course does not cover the entire domain yet, we also have defined two examples of application ontologies, one for the tensile test and one for the heat treatment, which will be briefly introduced by my colleagues then after my talk here. So only to give you a structure of what we did so far and what we are talking about. The question, of course, is how do we solve this huge task to get or to come to a domain ontology that we need, that we connect then onto all our application ontologies? Of course, we should follow an approved methodology, meaning we're starting with something and in the end we come up with a great ontology. And as you see here, there are lots of different, also already approved methodologies, and it depends, exactly on what you are doing, which methodology to follow. So it also depends on the scale of, let's say, the ontology or the domain you are working in. And is it only a toy example, or will it be highly elaborate? How many people are interacting there? What tools are used there to interact and to implement the ontology? Are design patterns, for example, existing that you can build upon? So there are lots of different ways to define efficiently ontologies, and this is also something which is, let's say, research is not over there yet, so people are not completely happy with everything what is out there. It works for some applications, and by applying one of these ontologies then for your application, you will see, okay, each of them have some shortcomings and they can be improved. This also holds for all of the existing tools for ontology design, especially if it comes to collaborative ontology design. Thereby, take-home message here, number one, it is really, really important that you know what's the purpose of this ontology you are designing here. So what will be the applications that will be driven by the ontology? What should they be able to do? Is it simply that you are, let's say, able to integrate research data from different sources to join them, to integrate them, and to build something upon them, using them jointly? Or is it even more complicated? Do you want to, let's say, do simulation and want to verify your simulation results by checking consistency of these results, or by explaining them, for example, with the help of an ontology? So this is another thing that you can do with the ontology to enable explainability, for example. So it really depends on the kind of application you have in mind and what is exactly the purpose to see how this works. One of the things which is really important that you can do is, of course, I already said, so data integration for integrating ontologies in huge information systems, where you then have the possibility to apply semantic search and retrieval, which means you search not only by string similarity and string matches, you can do then semantic similarity and semantic matches. And also you can look for relatedness of things, which thing is related with what thing. So you can see this in these knowledge graphs, which are constituted from the data that has been put into the ontology schemas, and thereby following these graph paths, you can also use this for explain and explanation of your search results, for example. So exploration and recommendation is another example. So you can show how your data.
Harald, you're already 7 minutes
30 seconds.
over the time.
I'm very sorry, 30 seconds. So you can use it for exploration and recommendation. And the last thing that I already mentioned is consistency checking and prediction, which is also one of the goals of PMD. And by that, I'm very sorry that I took so long. So thank you very much for your attention. And probably you have lots of questions left that we might answer later.